Okay, let's move to metamorphic rocks. And remember, the characteristics that we want to use to identify rocks will be looking at the texture. That is, looking at the grains in the sedimentary rocks, assuming we can see them. Sometimes you can't see them, but when you can see them, the key thing is the size of the grains, their composition, and their shape. Okay, so 3 characteristics of the grains. Now, let's see what would happen to a detrital sedimentary rock. And let's say we started out with sandstone. Now, actually, we have this rock because one important thing to remember when you're looking at rocks is you want to look at a fresh surface, one that's been broken recently, because that tells you what's inside the rock. Many rocks will develop a veneer of rust on them or some other coating of things that sort of makes it difficult to figure out what's inside. Clearly, this is a bit reddish, so it must have some iron. And we'll talk more about weathering reactions later in the semester. But when we look at the fresh material, you can see, well, this rock seems to roughly break in planes. And so that suggests that there must be some layering present. And you can just barely see little grains in there. And so you say, oh, well, what is it? Let's, one of the tricks you can do is sometimes you tap on these rocks. They really have kind of a high-pitched ring to them. And so that's a clue that maybe it's been crystallized a lot. And indeed, this is probably recrystallized sandstone, which gives us a rock called quartzite. Okay, if we don't expose things to quite such a high temperature and pressure, we might get a rock like this. And notice, oh, look how shiny that is and how smooth. This is a rock called slate. Oh, we can make a blackboard out of this. All right, this is what happens to shale. So you metamorphose the all the clay minerals that are in the shale, and they get stronger, slightly bigger crystal size, little change in chemical composition, and we have shale. But again, notice how easily this breaks on certain planes, and so this too could be a dangerous rock to build on if it's dipping down slope. If we keep metamorphosing, then we might get to a rock called schist. And so schist is comes from clays that have a lot of aluminum in them. And as we heat those up and add pressure, turns out you'll recrystallize that into muscovite and biotite, those sheet silicate minerals that we talked about in the minerals lab. And so we have just a whole bunch of sort of very reflective surfaces of that mica. And you can see the very fine layering. This turns out to be a rock that is going to be important to us later on. This is called the Polona schist. And this rock failed, leading to an enormous dam disaster that we'll talk about later in the semester. But you can see why, because here you've got all of these planes where the muscovite is concentrated and oriented. And so here you've got very nice layering, but it's much more crystalline than we saw in the slate or in the shale. And so we know that this has been heated to a higher temperature, causing recrystallization and metamorphosis. Now, another rock that we can get is, let me take a look at this. Now, this is a rock that you looked at last time. It's an igneous rocks. And you notice when you look at the grains, you can see the crystals. So what does that make it? Is it volcanic or plutonic? Intrusive or extrusive? Well, remember that crystal size tells us about how slowly it cooled. And so this must have cooled slowly deep in the earth. It's a plutonic rock, and it's granite. Okay, you can see the crystals in there. And notice how those crystals are angular and they interlock. So that's a characteristic that allows you to distinguish these igneous rocks from, say, a sandstone or perhaps some other rock, a conglomerate that was big enough to have crystals that you could see with the naked eye. If you were to apply enough pressure and heat, turns out you could make the minerals reorient and wind up aligning themselves as bands. And so here you can see this is clearly a foliated rock and with bands which look like layers, but the crystals are big enough that you can see them. And so, in fact, oh, this rock is really nice, isn't it? You're supposed to get the joke and say, oh, that rock is nice. While it is N-I-C-E, it is actually spelled G-N-E-I-S-S. Gneiss, or properly pronounced nice. So this is what you get if you metamorphose a granite. And finally, we come to a very important building stone that is often used in floors and sometimes in walls. And so when you look at this, you say, oh, look at these crystals. You can see the crystals. And they are all interlocking. So you say, oh, is this igneous? Well, if we test the hardness of this, okay, so we got some powder. Oh, it brushes right off. Mm-hmm. Look at that. Softer than steel. And if I put acid on this, it would bubble like crazy. So we know that this must be made out of calcite. How do you get calcite with such beautiful crystals? Well, you can have metamorphosis. And so if we take this limestone and we apply heat and pressure, the calcite in this limestone is going to recrystallize to give us beautiful marble. So that's the rock marble. Here's its sedimentary equivalent. So that's a run through rocks, and hopefully you've gotten a good sense that if you look at the size and composition and arrangement of the grains in the rock, that would be the texture, and you have clues for figuring out what type it is. If you see layers or bands, then you know it's igneous, or I'm sorry, you know it's sedimentary or metamorphic. And the arrangement of those and the size of the crystals is going to distinguish metamorphic rocks with bigger crystals from the sedimentary rocks, which generally have smaller crystals, with the exception of sandstone and conglomerate, but they look very distinctive themselves. You can distinguish igneous rocks because they often have crystals that are big enough to see that are interlocking. Now, of course, rhyolite and basalt are different than that, but again, they're pretty characteristic in terms of, here's rhyolite, pretty characteristic in terms of its nature. And sometimes you'll see these tiny little crystals in rhyolite that crystallized before this rock was extruded. And so those are randomly oriented. They aren't in nice layers. So I hope you've enjoyed this tour through the rock world and you've been successful at finding some fun rocks, and you're now busy identifying them. So look carefully, describe what you see, and then think about what the implications of those observations are.
All right.